In this section, we will look at eigenvalues and eigenvectors of linear transformations from that map V onto V, one vector space onto another. In the case where V is a finite dimensional vector space and there is a basis for V consisting of eigenvectors of T, the linear transformation, we will see how to represent the transformation T as a left multiplication by a diagonal matrix. Definition: let V be a vector space. An eigenvector of a linear transformation from V to V is a non-zero vector x in your vector space such that the transformation of that x is equal to lambda x, lambda being your eigenvalue, and it will be a scalar. So lambda tx equals lambda x for some scalar lambda. A scalar lambda is called an eigenvalue of t if there is a non-trivial solution x such that t of x equals lambda x. And x is called an eigenvector corresponding to lambda, your eigenvalue. The matrix of a linear transformation, let V be an n-dimensional vector space, and let T be any linear transformation from V to V. To associate a matrix with T, choose any basis for V. Given any x in the vector space, vector x, the coordinate vector x sub b will be an Rn. Those will match as the coordinate vector of its image. The image is when you put it through the transformation, and it'll be representing that basis. The connection between x sub b and t of x sub b is to let b be the basis for v. If x can be written as r1b1 plus all the way through to rnbn, then x sub b is just a vector column of the weights. And t of x is the transformation of that vector. And because it's linear, these weights or constant values can be pulled out. So it takes on the form R1 times your transformation of B1 all the way through weight in Rn times the transformation of Bn. Now, since the coordinate mapping from V to Rn is linear, you can write all this as, instead of t of x, you have the t of x b coordinate. But anyway, you take the same expansion as up here, but your weights will just be out front. So it'll be the image of b1, the image all the way through until you run out of vectors, essentially. Since b coordinate vectors are in Rn, the vector equation above, this one, can be written as a matrix equation. T of x sub b is equal to matrix, some matrix times the b coordinate vector, where m is the list of all vectors of the transformations, and it'll be denoted with a t in a bracket and a subscript b. This matrix M is a matrix representation of T called the matrix for T relative to the basis B, and it's denoted by T sub B. Okay, so finally getting into some examples. Suppose B is a basis for vector space V where B has two vectors inside in the set. Let T be a linear transformation from V to V with the property that the transformation of the first basis vector is 3b1 minus 2b2, and the image or the transformation of the second basis vector is 4b1 plus 7b2. Find matrix M for T relative to B. Basically, we're looking for a matrix that represents the transformation from a vector to its image. The b coordinate vectors of the images of b1 and b2, basically you take the coefficients. Now since the basis only has 2 vectors in it, you only go 2 units deep. So the b coordinate vectors of the images of b1 and b2, and when you see images, it's what you get after the transformation. So 3b1, negative 2b2, and then the transformation of the second basis vector was 4b1 plus 7b2. And what we'll do is we'll take those and make them columns. And there was the first slide had the formula for that matrix. It's just really ugly looking. So basically you find if you know your images, you take the coefficients out, vertically stack them, and then take each one in order and make vertical columns of those numbers. All those columns will make up your matrix M. Second example, the mapping of t from a second degree polynomial to another second degree polynomial defined by t of a sub 0 plus a1t, that's a linear term, plus a sub 2 t squared, and that's a quadratic term, is equal to, once you transform, in the parentheses you're at this spot. After the transformation you're over here. a1 plus 2a2t. If you've had Cal 1, and I assume you have if you're in linear algebra, this transformation is the derivative. The derivative of a constant is 0. The derivative of a linear term is its coefficient. And then the derivative of a quadratic would be 2 times a sub 2 t to the first power. Okay, so we know the transformation is a derivative. Part A to this is we're going to find a B matrix for t when B is a basis for a second degree polynomial. So we have a constant, a linear, and a quadratic term making up the basis. Now because there's 3 parts to each term, like a constant, you have a constant, no linear, no quadratic. That's what this part means. Compute the images, and that's what you would get after the transformation of your basis vectors. So we're going to do them one at a time. We're going to take basis vector 1, representing the constants, the transformation of 1, which it's a constant, and we know that that's defined as a derivative. What's the derivative of 1? 0. Very good. Now, to represent 0 with 3 terms, you just put a column of 3 zeros. The transformation, the second basis vector is t. What's the derivative of t? 1. Just think of it as if I'd ask what's the derivative of x, it would be 1. So your transformation of t is equal to 1. That basis vector would be 1's a constant. You don't have a linear, you don't have a quadratic. And then finally, the third basis vector is t squared. Its derivative, because that's the definition, would be 2t. Transformation of t squared is 2t. Now that's a linear term, so we have 0 for a constant. There's no constant. 2 is the coefficient of the linear term. And then we don't have a t squared, so 0 for the t squared term. Once you've transformed all 3 of these basis vectors, in order, take these 3 and put them in a matrix. And that's your B matrix relative to t. Verify that for any polynomial, the transformation of that polynomial is going to be equal to your transformation matrix times the basis of your polynomials. For a general p of t, and again, remember this is for any polynomial of degree 2, You have a constant, linear, and quadratic terms. You don't always have to have all three, but all three could be in it. So what we'll do is for any polynomial, if you take the derivative, your constant drops out. Your linear term, you keep the coefficient. And for the quadratic, it's 2 times t to the first. If there's a number here like a 5, then you do 5 times 2, which would give you 10t. But we don't know what that number is specifically. So it's 2 times whatever the existing coefficient it is, times t. Now, to write that as a vector, constant, linear, and there's no quadratic. There's no t square in here. So we're going to take our vector from the previous slide, matrix from the previous slide. That's the one we found at the end of the previous slide, times any general basis vector, constant, linear, quadratic coefficient, and that's what we get, is we get the B matrix times the polynomial basis. Theorem, diagonal matrix representation. Suppose A can be written as some matrix P times a diagonal D times P inverse. And we dealt with that in a previous section where we would have eigenvectors making up P, eigenvalues being the diagonal of D. But D is a diagonal for an n by n matrix. If B is the basis for Rn formed from the columns of P, then your diagonal matrix is the B matrix for that transformation from vector X to matrix A times vector X. Example, defined the linear transformation from R2 to R2 by transforming X, T of X, that's going to be equal to matrix A times that same vector X. A is given as a 2 by 2, so we're going to find a basis B for R2 with the property that the B matrix for T is a diagonal matrix. From previous sections, you can determine that the eigenvalue 5, and on the next slide I actually write all this out. This is just shorthand notation to get to the meat of it. But anyway, this matrix has two eigenvalues, 5 and 3. For 5, you get an eigenvector of 1 and negative 1. This little asterisk shouldn't be there. I think I meant to delete that and I just didn't, or white out over it. The other eigenvalue 3 corresponds to 1, negative 2. So knowing your eigenvectors, 1, negative 1, that's your first column. 1, negative 2, that's your second column. And then each eigenvalue in the same order, 5 corresponds to that eigenvector. And then eigenvalue 3, second column, corresponds with that eigenvector. The similarity of matrix representation, if A is similar to matrix C with A equal P times C times P inverse, then C is the B matrix for the transformation from X to AX when the basis B is formed from the columns of P, similar to what we just did. Conversely, if your linear transformation from Rn to Rn is defined by Tx equals Ax, and B is any basis for Rn, then the B matrix for T is similar to A. And so think about this. Once you switch over to your B matrix, you can invert out front and swap places, P inverse A, P. Note, the set of all matrices similar to matrix A coincides with the set of all matrix representations of the transformations from X to A times X. For example, let's let A be a 2 by 2 matrix, B1 is 3, 2, and B2 is 2, 1. The characteristic polynomial of A, if you were to use the processes from earlier sections, you would get lambda plus 2 times another lambda plus 2. Well, if you set this part equal to 0, you get an eigenvalue of negative 2, and it has a multiplicity of 2. The problem is, for this one, this eigenvalue only produces is one-dimensional. The eigenspace for this particular eigenvalue is only one-dimensional, and that just means that A is not diagonalizable. However, your basis, vectors B1 and B2, has the property that the B matrix for X mapped to AX is a triangular matrix called the Jordan form of A. Let's find this B matrix. Okay, so P, if you're given these B matrices, B1 and B2, you stack those in here. That's B1, B2. So your B matrix is going to be defined as P inverse times A times P. This part, A times P, gives you this 2 by 2 matrix. So let's remember that. And we're going to left multiply this one by P inverse. P inverse, you can just use your calculator. Take matrix P from the previous slide, put it in your TI-84 or online calculator, invert it, you will get this 2 by 2. So to get our B matrix, this inverse times the result from AP, we did that on the previous slide. These two multiply out, P inverse times AP gives us this 2 by 2 matrix. Notice our eigenvalue is listed on the main diagonal. Okay, so to go back and fill in some of the gaps, because a lot of that was real quick, wave hands and claim magic, basically. Recall that A was this 2 by 2 matrix, and this is just a review of previous sections, but it never hurts to see it more than once. All right, basically what you do to get your eigenvalues is you take your matrix, subtract lambda times the identity matrix of an appropriate size, so A minus lambda times the identity matrix, we get this 2 by 2. Now, take the determinant of this 2 by 2 matrix, so we have, and I use, again, vertical bars, 4 minus lambda times negative 8 minus lambda minus negative 9 times 4. FOIL, you get negative 32 minus 4 lambda plus 8 lambda is positive 4 lambda plus lambda squared plus 36, and then when you put your like terms together, you get 4. Write this in descending order. Lambda squared plus 4 lambda plus 4. That factors into lambda plus 2 twice. This is either one, written separately or together with a power of 2. That's your characteristic polynomial. When you set that equal to 0, that's a characteristic equation. And then when you finally solve, that's your eigenvalue. Lambda equals negative 2 is an eigenvalue of multiplicity 2 because it shows up twice. Now, remember, to find basis vectors, you take A minus lambda I. You augment it with a column of zeros, and then you row reduce. So, not to go too fast, if you take your time. You take matrix A from the beginning and add 2 times the identity matrix. So here's matrix A. Since you know that lambda is equal to -2 minus -2, that's where I'm getting this +2. It'll be opposite of your eigenvalue sign. So 4 plus 2 is 6. -8 plus 2 is -6. The other diagonal stays the same because you're going to add 0 to it. Augment with a column of zeros and row reduce. This tells us that 2x1 minus 3x2 is equal to 0. Well, if you carry this across, 2x1 is equal to 3x2, and then divide by 2, x1 is equal to 3/2 x2. There is no pivot in the second column, so x2 is free. Writing your vector as x1, x2, x1 is 3/2 x2, x2 is free. Factoring out, it kind of looks like you factor out x2. That leaves you with coefficients 3/2 and 1. And so there's your result. On Google Drive, I did put homework solutions to each of the 6 problems that are in your homework assignment. I know this video was a lot of vocab and a lot of jargon, not as many examples as I like to do. So you'll find this in Google Drive as a document you can refer to and print. I did put a separate one in there right below this one that is strictly homework examples being written out. And feel free to use that as much or as little as you like. And that I tried to do an example of each one that you'll see in your homework set. Of course, you won't have the exact same numbers, but it should be very close. And I did a lot of steps in between so that you can try to make heads or tails of some of this stuff. But anyway, let me know if you have questions, and just hang in there with it. We're almost done.